Hi everyone. I think we will have to start, but then we are expecting quite a number of people to join today's section. We have about 40 people on the call now, but then we would have to start. So first of all, I'll just follow the protocol. I would like to thank the bioconductor team, the H3 team, and the H3Africa coordinators of the team for working together to put up this free virtual workshop. So today is the day 2, and we will be having a workshop on the epidemiology for bioinformaticians. And we have 3 trainers on the call now. And I would like to give a brief intro of the trainers. So we have Chloe. So Chloe is a data scientist and a doctoral candidate in epidemiology at the City University of New York, Graduate School of Public Health and Health Policy. She has experience designing, implementing, and maintaining data collection, management, and creation of tools on a variety of projects, ranging from large national core studies to other projects such as COVID-19, microbiome, HIV, and mental health. Her research interests are focused on the role of microbiome on human health, causal inference in microbiome research, and improving the epidemiological rigor of health and bioinformatics research. Her dissertation will focus on the impact of antibiotics on the human gut microbiome. And her mentor is Levi. Levi was on the call yesterday as one of the trainers. I would also, we have Sean Davis on the call already, and he also participated in yesterday's section, but then for those who are unable to join us yesterday. So Sean Davis is a professor at the University of Colorado Ashute School of Medicine, and he received his BS Bachelor of Science in Mechanical and Aerospace Engineering from the Princeton University and his MD and PhD from the University of Pittsburgh in the Schools of Medicine and Public Health, respectively. He completed his residency in pediatrics at the Children's Hospital and Regional Medical Center, followed by pediatric hematology and oncology training in the Johns Hopkins School of Medicine, National Cancer Institute Joint Fellowship. So without much ado, I would hand over to Sean Davis, who will then hand over to Chloe, then we will start from there. Once again, thank you for joining today's section. Right.
All right. Good morning, everybody. It's around 6 a.m. for me. I know it's a much more normal time for most of you. So bear with me. I haven't even had a cup of coffee yet. I'm really looking forward to hearing from Chloe. I've heard this talk a couple of times, and it's off the beaten path for me. I learn something new every time. So I'm very excited, and I hope you are too. For those of you who haven't attended one of these kinds of things before, we try to keep it as informal as possible. So feel free to use the chat. Feel free to pipe up, and I'll be putting a couple links in the chat box as well about how to join the bioconductor community, and in particular the Slack channel, so that as we finish up today, you're prepared to communicate with each other as you see fit. We actually have a H3Africa channel, so feel free to join that and start to build your own networks. and also just more broadly to get connected to the bioconductor community. Moving a little closer to the day or the morning, my morning, we have a set of materials that Chloe's going to talk through in more detail. For those of you who want to follow along, follow along with the materials hands-on. We have a couple of options. One, Chloe's materials are relatively straightforward to install and use if you want to do stuff on your laptop. For you to do that, you would need the most recent version of R, which is at least version 4.0. Ideally, you'd want RStudio installed, and Chloe will talk through the packages that you'll need to install as well, and how to get the materials. The other option is we have these materials online, ready for you to use. And if you want to do that, I'm going to show you very quickly how to get an RStudio and R instance running in the cloud, so no installation necessary. So I'm going to go ahead and start with that, and then once we get through that, get people logged in if they're interested, then I'm going to turn it over to Chloe. So let me share my screen really quickly here. And sorry about the clutter, but in the chat, I've put a link to app.orchestra.cancerdataSci.org. And if you type that in or click on it, what you'll get is this. There's only one way to go from here. It's log in to get started. You have two options: sign in with a Google address, a Gmail account, or sign in with email. If you sign in with email, obviously most of you won't have an account already. You'll type in your email. You'll get an email from the application saying, continue, and then you can go ahead and continue and create your account. I have a Google account, Gmail account, so I'm going to sign in with that. If you have a Gmail account, you can do that as well. It'll look very similar to what I'm going to do. So I'm going to click sign in with Google. Actually, I'm going to jump over. So at this point, I would have signed in, and I'm going to jump over to my other window here. And you'll end up in a page that looks like this. Choose a workshop. And there are about 50 or 55 workshops available now. Any of these you can use anytime that you like. The workshops, once you start one of them, will last for 8 hours right now. If it turns out that you start one and you don't finish it, you can come back tomorrow and relaunch. You'll have to start over from the beginning, but my point is you can reuse, or you can come back to these anytime you like. Once you're on Choose a Workshop, you can start searching for something that's interesting. I'm particularly interested in epidemiology for bioinformaticians. That seems really exciting to me this morning. So once you're here, there are two links now that you can use. This link will take you to Chloe's workshop material that I've beautifully put together here. This is what she's going to be following along with. If you're going to be doing this at home, this is where you might want to end up on your laptop. If you're going to be following along in the cloud, then you're going to want to click Launch. And you'll see the little bar at the bottom of my screen. What's going on right now is that Google is setting up an RStudio instance for you. And once that little button launch workshop is ready, we're going to click on it. Notice that the username and password are super secret. RStudio and RStudio. It's the same for everyone. So I'm going to type RStudio. Sign in. Google is going to complain about checking passwords. I think I might have typed this wrong. RStudio. And what you'll get then is an RStudio instance. This is the same RStudio that you'd be running locally. It's just running in the cloud instead. Everything that you would want to do on your laptop, you can do here as well. And to kick things off, there's a files menu in the bottom right here. If I click on vignettes, we're going to see that there's this file called Epi for bio workshops. If we click on that, that's going to open this R Markdown. This file, once we run it through R, actually generates this document. So this document and this document are the same. So as you're following along, you can use cut and paste here. You can also hit Control and Enter for each line. And you can see in the bottom left-hand corner, what that's doing when I hit Control Enter is essentially copying and pasting the line into R. So it's a quick way to follow along with Chloe without having to do a lot of typing. So this is cheating to do the cut and paste, but it's also fast. So I encourage, if you're using this kind of method of doing this cutting and pasting, that you come back later and experiment a little bit with each of the steps. So I feel like I've talked too much already. So I'm going to turn things over to Chloe. Feel free to ask questions in the chat about that process, and I'll do my best to respond. So have fun, Chloe, and looking forward to it.
So good morning, everyone, and morning for me. I'm also in Colorado, so it is 6 a.m. here as well. I'm so excited to be here. Thank you all so much for having me, and thank you to Francis and to Sean for their wonderful introductions. As Sean demonstrated, you can follow along using those materials. I'll also put in the chat now links to the latest version on GitHub if you prefer to follow along there, as well as the GitHub pages. I am the type of person who is constantly making small changes to my presentation up until the last minute. And so if you want just the 100% most accurate, up to the minute version, it is available on the GitHub repository or on the GitHub pages link, which is the link on my website, which you can see in chat. I will share my screen now, and we'll get started. So the first thing I want to say is I'm going to have chat open, if I can get it, there it is, on my other screen. So if you have any questions or comments, please drop them in there. I'll be looking over at it every so often, and I really want this workshop to be interactive. Often I've given it before, and when people have questions or comments, I feel like that really enhances things, because I have my perspective on how epidemiology and causal inference work, but I've always found that people have some really interesting insights. They they bring a lot to this. So please, use that chat function. I am looking at it, and we can talk about it. So um, welcome to Epidemiology for Bioinformaticians. My name is Chloe Merzai, and I wanted to start with probably the most famous causal inference problem kind of in history, and that is smoking and lung cancer. And I don't think anyone here today would probably be surprised to hear that, we're pretty sure that smoking causes lung cancer. There's a lot of evidence, but how did we get there? In the present day, we've accepted this fact, but it was incredibly controversial in the 1950s and the 1960s. And in fact, the famous statistician R.A. Fisher, who developed ANOVA, the F distribution, odds are if you do any statistics, you've probably used a method that he invented. He believed that smoking did not cause lung cancer. And he was probably one of the first people to really take up this rallying cry that we hear so often, which is that correlation does not equal causation. So R.A. Fisher really spent the 1950s and the early 60s arguing that just because they found a link, this association or correlation between smoking and lung cancer, just because they found that link, that doesn't mean that it's a causal link. It just could just be, an association that doesn't mean anything. Uh, R.A. Fisher was also an avid smoker who took money from the tobacco industry. We know that now. So he had his own ulterior motives. But I think this problem of smoking lung cancer, which we now know to be so obvious, raises some really interesting questions to consider. So the first, these are things to think about. I don't expect you to have answers now, although if you do have an answer, that's great, but just something to think about. Well, the first, if you wanted to prove Fisher wrong, this famous statistician, and you wanted to demonstrate smoking causes lung cancer, how would you do so? And then my second question to think about is, one of his main arguments was that there was a genetic factor. There was some genetic variant, some kind of gene that was causing both people to smoke and for them to develop lung cancer. So there was this common cause that would create this, artificial association between smoking and lung cancer that didn't actually exist. And he argued that this genetic factor was what was truly causing lung cancer in smokers. So if that theory, if you wanted to test that theory, Fisher's theory of this common factor, this genetic factor, how would you do that? And again, you don't need to have an answer for these questions yet. We'll talk about and how to answer them kind of later on as we go through the workshop today. So to now back up a bit, after giving you that teaser, and talk about some of the goals and the outline for this workshop. The first thing I'm going to do is introduce some fundamental concepts of causal inference. Then we'll discuss how to make directed acyclic graphs, otherwise known as DAGs, and how to use them when analyzing data. We'll explore concepts of bias and confounding, review common study designs and their implications for causal inference, and briefly look at some tools in R that can help with causal inference. Along the way, there'll be plenty of questions and exercises for you to follow along with. And again, just if you have any questions or comments, please just throw them in the chat. And I am looking at it, and probably, because I know Zoom can be a little fatiguing, we'll take a break about halfway through the workshop. So to get started, I think the first question is, what is a cause? What is, we're talking about causal inference. What does it mean to cause something? And I'm hoping, if I'll give you a few seconds, if you could just drop in chat in your own words, what is a cause? What does it mean to cause something? And put those answers in the chat. Uh, David says an agent that affects a system. Yeah, that's a great way of thinking about it. It's something that affects a system, that changes something in a system. Winfred says a factor being on the pathway leading to a given outcome. Um, Wobble. I'll apologize in advance. By the way, I have a speech impediment, so uh, some names are really difficult for me. So I'm really sorry if I butcher your name. It's not on purpose. I just have a bit of a speech impediment. Um, a cause is a direct or indirect effect on the body. Yes, that's great. Yeah, it's something. I like the idea of an indirect effect because it could be that it causes something that causes something else to happen. So that's a really good way of putting it. Elizabeth says being responsible for something happening, and Nyangiri says to make something happen. I think those, yes, similar. Yeah, it's making something happen. Uh, Javen says something that changes the function of the system entity. And I see some more answers, but I won't go through them all, but thank you all for answering. Those are all great answers. You know, we believe it is something that brings about an effect or result. It can be in a larger system. It could indirectly bring that about. These are all, you know, important parts of a cause, but you can see it's kind of complicated. It's kind of difficult to say what it actually means in simple words sometimes, especially when we think about it less on, you know, like the macro level and start thinking about it in the human body. Um, but despite, you know, sometimes that's difficult to talk about, I think we actually have a relatively, you know, good understanding of causation when we observe it directly. You know, like when I touch a stove while I'm cooking and I burn my finger, I'm pretty sure I know what caused my finger to get burnt. You know, I touched the hot stove, and then you I could also trace it backwards and say like, well, why did I touch the stove? Maybe I wasn't paying attention, and but why was the stove hot in the first place? Well, because I was cooking dinner. And why wasn't I paying attention? Because of the antics, you know, of my cat running around, let's say. So these direct and indirect factors uh, affect what we see, you know, what the causal pathway that we see in real life, and we can really intuitively see this ourselves. Um, but it becomes a little less intuitive when we think about it in terms of our own work on this level that we can't necessarily directly observe. Um, so my next question for you, and again, just drop this in chat. Uh, what are some causal questions you may be interested in in the context of, you know, your field of work or study or research, bioinformatics, or any related field? You know, just drop what are some causal questions you're interested in. Um, for myself, you know, like I'm very interested in the role of the gut microbiome in human health. You know, I think a lot has been written about how these potential, you know, pathways by which the microbiome might cause all sorts of things, from various forms of cancer to mental health issues to uh, you know, conditions like chronic conditions such as diabetes. You know, we think that the microbiome might have like a causal role, that if the microbiota in your gut microbiome changes in some way, that this might either cause these diseases, or it might exacerbate the symptoms of these diseases, making them worse. And so that's what I'm really interested in. I'm seeing a few answers come in. David says they're interested in variants affecting disease risk. Reagan says, what makes some people to die of COVID-19 and others to survive? That's a really good question, you know, and a really important one right now is just, why do some people, you know, and I think we've all heard of cases of people who were very healthy, ate well, you know, athletes in their 20s and 30s who have passed away from COVID, whereas, you know, some people, you know, you also hear cases of people who are in their 90s or even their hundreds who survive or have a very mild case. And so there's a whole question, why did, you know, why did they have such a disparate response to COVID-19? So Yeah, that's a great example of kind of a causal question. And Winfred says, harnessing genetic variants for drug repurposing. Yeah, so that's also important as well, is determining how genetic variation might affect how we respond to certain drugs and medications. Um, and Wobble says, how in utero HIV exposure can causes immune alterations. That's great too. Yeah, in utero HIV exposure is something that is really important to study, and yeah, understanding how it could cause alterations in immune system function kind of across the lifespan for a child that was exposed in utero could be a very important causal question to explore. Um, yeah, so I see a few more answers coming in. I think these are all great, so thank you, and continue to put answers in if you would like. So these are all important, causal questions. And but one thing that makes this difficult for a lot of these questions, we can't directly observe the event of interest. We can't usually, cut someone open and say, okay, what's going on in their gut microbiome at every exact moment, and can we follow along, whatever these mechanisms or pathways that we're interested in. Instead, we have to draw inference based on data collected at time points and try and infer kind of what has happened along the way. We don't have 100% picture of what's going on at every given moment inside someone's body. And same case for COVID or for in utero HIV exposure for genetic variants. We can look at it at certain time points, take a snapshot, and then try and infer what happened, but we don't really get to follow along continuously as it goes through a pathway. So instead, of defining, causality in a dictionary definition, or, kind of our own words, what we can define it using is a counterfactual. And what this means is this definition of a cause says, what would have happened had the event of interest, whoops, I doubled up the language, had the event of interest not occurred. And so what would have happened had the event of interest not occurred? And that is a little confusing. So I'm going to give an example. So I lived in New York City for a long time, so this example is common. So a dog and an ambulance. So an ambulance drives by a house with its sirens going, it's making a lot of noise, and a dog in that house's yard barks. And we can ask a very straightforward causal question. Did the ambulance driving by the house cause the dog to bark? Um, but that question, to me, it's a little ambiguous. Like, where do we go from there? What's the research question there? So what we can do instead is then rephrase that question in terms of a counterfactual and ask, would the dog have barked if the ambulance had not driven by the house? And that kind of leads us to an experiment. We could say, okay, well, this question to me is saying, well, what we need to do is get a bunch of ambulances and drive by a bunch of houses with dogs, see if the dogs bark, and then we need to go at another time and not drive by those houses and see if the dog is barking. And effectively what we've done there is a randomized clinical trial where we've, I guess, looked at whether the ambulance is causing the dog to bark. And to me, that's the power of a counterfactual question, is that it leads us to the study design that we want to test whether this is true or not. So some more examples. So a very common causal question that I think is being asked all over the world right now is, does the COVID vaccine increase the risk of blood clots. We've seen with, I believe, AstraZeneca and Johnson & Johnson vaccines that regulators are worried that they increase the risk of blood clots. But let's rephrase that question in terms of a counterfactual. And we could say, would people have developed blood clots if they had not been given the vaccine? And in my own research, I could say, does the gut microbiome cause colorectal cancer? And then we could say, would these people have developed colorectal cancer if their microbiomes had not changed? Would be the counterfactual equivalent of that question. And so next question, again, to drop in chat, using the causal question or causal topic of interest that you've just thought up, reframe it in terms of a counterfactual and just put that in chat. I know this takes some thinking, so I'll give people a few moments to think it through. Okay, so we got our first answer from Reagan. Would the COVID-19 victims have died if they did not have the supposed risk factors? Perfect. That's a perfect kind of counterfactual question. And again, it leads to a very natural study design in that we say, okay, well, we need to do a study where we look at people who have the supposed risk factors, compare them to people who don't, and look at the mortality rates in those two groups and see how that changes. So that's a great example of kind of the counterfactual definition of a causal question. So David says, does integration of data sets improve inferential accuracy? Is that a question or is that an answer? I'm not sure, but Winfred says, would more students have opted for bioinformatics training if programming course was exempted? Yeah, that's a good question. Would more students have opted for, yeah, I mean, some people don't want to learn to program. Oh, is a question and an answer. Yeah, does integration improve inferential accuracy? So yeah, would the integration of data sets improve the inferential accuracy of some question? Yeah, that is a good way of saying that. Javen, what do you say about the dog example? Yeah, so the dog example again is, would the dog have barked if the ambulance had not driven by the house? That would be the counterfactual question. A reframing of the question, did the ambulance driving by the house cause the dog to bark? So these are good examples. Thank you so much again for everyone putting these in chat. And something to continue to think about is this definition of a counterfactual, because I think it's important because it leads us to the study design. So we'll move on. So next we're going to talk about, so we've talked about how to kind of define our causal question. So now that we have a question, the next step is, well, okay, now how do we answer that question? And one tool that can help us is called a DAG, or a directed acyclic graph. So we can call this also a causal diagram. And here's what it looks like in its simplest form. We've got the example from earlier. We've got our ambulance, and it causes the dog to bark, or at least that's our theory that we want to test. And so we draw this. The ambulance is our what we might call our exposure or our event of interest, and the dog barking is our outcome or kind of effect of interest. And we draw an arrow between them because we believe that the ambulance is causing the dog to bark. This is different from a statistical diagram because we must state a directional relationship. We must have an arrow. We must say that one causes the other. Technically, there are more complicated systems we know in biology of like feedback loops, and where maybe the dog barking, uh, well, somehow that causes more ambulances to come, and that causes the dog to bark even more. Um, that doesn't really make sense, but in biology, there's more examples of feedback loops. Um, but for our purposes, these are supposed to be one directional in a DAG. That's why it's acyclic. That means we don't have any cycles in it. So instead, what we're proposing here is that one cause leads to one effect. Um, and this is the simplest form of causal diagram. It only has two variables. Um, and if we were to want to, let's say we wanted to model this relationship, so we want to test if this relationship was true, it would be a simple, regression model. We would enter two variables. We would have our independent variable, which would be the ambulances driving by, and we would have our outcome, which would be the number of dogs barking. And if this was truly, the true causal model, the complete causal model of this relationship, um, we would get an unbiased estimate of the actual strength of the cause on this effect. So, if we saw, that an ambulance driving by caused about 80% of dogs to start barking, that estimate would be, and if this model were true, which um, we're not sure of, but if we believe this model to be true, then that would be a true unbiased estimate of that effect. However, as I'm sure we're all aware, in the real world, it's very rare that you see a situation where it's just one variable leading to another. There's probably a lot more going on. So just to think about our ambulance and the dog a bit more, one question for you is, can you think of any situations that may result in a bias to the observed relationship between the ambulance and the dog barking? That is to say, can you think of a situation where we might observe the ambulance driving by and the dog barking, and yet the effect would be biased in some way, or there's something wrong with it? So just again, any guesses, any thoughts, drop them in chat. No wrong answers to this question. I just love to know if anyone has any ideas on what might be happening here. Mediators, yes. Elizabeth says mediators. That's perfect. We could imagine that there might be, we've oversimplified. The ambulance, causes the dog barking, but there might be variables in this arrow that we don't, that we're just assuming are there and are assuming maybe aren't important or aren't relevant. Um, so I think one of those might be like the dog. What if the dog has hearing loss? Like the dog might be deaf and therefore can't hear the ambulance driving by, and that might affect whether it barks or not. So there's a variable in there that's assumed that the dog is able to hear the ambulance. So that would be a mediator, I would say here. Javen says distance between the dog and the ambulance. And again, I think that's another mediator of this relationship, which would be how far away the dog is from the ambulance. Yeah, I would imagine that being a mediator, kind of something lying within this arrow. Samwabel says time interval between dog barking and passing ambulance is fixed. Yeah, and again, I think, let me think about that. Yeah, I think time is important here. that might be like a common cause. So it might be something that both affects whether there's an ambulance there and whether the dog is barking. For instance, I could see, you know, depending on the time, maybe the dog is asleep and doesn't wake up to hear the ambulance, or maybe the ambulance goes by and the dog was eating and it doesn't look up. So time could be important. Oh, here's a good, Winfred, this is great. What about if the dog saw an intruder at the same time the ambulance passes by? Yeah, there could be some other variable that's causing the dog to bark, right? It could just be that we observe this due to random chance. And this is what Tendai is also saying too. Any other stimulation that might cause the dog to bark, such as like an intruder. So that's great. Already you guys are thinking in terms of kind of causal variables here, and this is excellent. These are great answers. And so yes, there could be some lurking variable. I especially one other example I'd like to mention is like maybe there's something that is causing both the ambulance to be in the area and the dog to bark. So we can imagine if there was maybe a fire, and maybe that is why the ambulance is in the area and also why the dog is barking because it sees the fire, and that variable could be there as well. And that's pretty similar to the intruder or the other stimulation. So now I want to detour for a moment and talk about how we actually make DAGs, because I think they're really important. So we could draw them by hand on a piece of paper, or you could use a software that allows you to make diagrams like PowerPoint or Word, have some basic diagram features. But there are some specialized options available online, and we can then bring these into R, which I think is really helpful. So we're going to look at one of these, which is called Daggety. Daggety has an online interface as well as an R package. And the benefit of the online version is that it's got a user interface that's really easy to use. And then you can then export that diagram from the online interface into R. And so don't take my word for it. We're going to, we'll do it together. So I will put a link to this in chat. So this is Daggety's website. You can see here, there's a downloadable version as well. They talk about the R code, which is available on the CRAN. There's some other stuff, but the important thing here is this launch button. And if we hit this launch link, we'll see we're given a default model like this. This is just a very, just their basic example of a model. But if we go up here to model to new model, we then get this. Can you hear me now? Okay, I think it's working. Sorry, my microphone cut off. I don't know why. So as I was saying, if we go up here to model, new model, we can see this empty screen. And if we just double click, or actually, sorry, single click, we'll get this thing that says name of the new variable. So this allows us to add a variable. So we'll add our ambulance. We'll add another variable for our dog barking. And then what we want to do is click on this variable for ambulance. This is our exposure. So we'll go up here to this little thing that pops up here in the lower or in the upper left corner and say, this is my exposure. We can go over here to dog barking and say, this is my outcome. And then you can, then you can. Can you hear me now? If you can, please put it in chat. Okay, perfect. So I don't know what's going on with my headset. Wireless headset problems. Thank you, everyone. So yeah, so I'll just start over real quick just to make sure you got all that. So if we click once, we can add a name of our new variable. So we'll say ambulance, and then we click again and say dog barking. And then if we click on the variable in the upper left corner, we can then say, this is my exposure. And then we can go to dog barking, click on that and say, this is my outcome. But we haven't proposed any relationship. We don't see an arrow yet. So if we select our exposure and then double click on or single click rather on our outcome, we then, get our causal proposed pathway here between the ambulance and the dog barking. We can add more variables. We can add as many as we like. So one thing that someone mentioned was the possibility of an intruder causing the dog to bark. So we could see something like that. And we just add that and say that causes the dog to bark. We can say, someone mentioned possibility of mediators. One was the distance between the dog. So we could add that here. And that I think would probably be a mediator, so we could connect that. And if we want to get rid of a pathway, we can just click on ambulance and click on dog barking again, and we'll see that that pathway disappears. And so now we've got our mediator here, and through that mediator, that affects whether we observe the dog barking. And then I'll add in the thing I suggested, which was like a fire, which might cause the ambulance to be in the area, and it might also cause the dog to bark. And we see also that things turn different colors. We'll discuss why that is in a few minutes. But the important part here is that we can start making our diagram, and you can see that it starts getting pretty complicated pretty quickly. We only have 5 variables right now, and this is a fairly simple system. We can add a lot more to this. Like, there could be other factors, like, the ambulance. We can imagine that there's other variables. Like for the ambulance to be there, it needs to be dispatched. And there's other things. You can start thinking about tons and tons of variables and come up with a very complete system of possible variables that could be affecting this dog's barking. And so yeah, it gets pretty complicated pretty quickly. So that's why it's nice that we have software that allows us to do this. And I find that the diagrams visually are really great for us because trying to put this all into words, I think would be very difficult. That you could write paragraphs and paragraphs just trying to explain what we've done here with like 5 circles and a few arrows. So these diagrams are really helpful in summarizing what we think is going on. Now to talk a bit more about some features of Daggety. So we've made this, we set our exposure. Whoops, I added another arrow there. We set our outcome here, and you can see down below, you've got this model code. And this model code is great because one, if we want to, save this, we can just save this model code and bring it back later and use it. But the other nice thing about this, if it'll let me select it, we can copy this, and we can actually take this into R and just load the Daggety library, which you can install off the CRAN using install.packages Daggety. I've already have it installed, but you could run that if you don't. And then we could say, okay, well, I've got this DAG object. I'm going to paste it in here. and let me just save that as an object. And then if we just plot that DAG object, it's a little messy. We'd probably have to clean it up a little bit, but you can see it's just the DAG I just made in Daggety, and I've just brought it into R really quickly just by copy and pasting it. I used this Daggety command in the Daggety package. I didn't change anything from this, and then I just ask it to plot it. But this plot isn't the most beautiful ever. It doesn't have the best options in terms of how we can change it. So there's also a really great package called ggdag. If you've ever used ggplot or any of those in that kind of family of visualization in the tidyverse, it follows a very similar. I think it uses the same conventions, and so we can actually take that object, the DAG object, and do use kind of the GG plot style conventions in plotting it and get something a little nicer looking, hopefully. I don't know why it's making them so small. There we go. So we can see that just very quickly, we've copied our DAG into R. Oh, yes, the Daggety script. I can post it. Yeah. I'll post the whole thing. So just very quickly, we went from, just playing around in the online user interface all the way to bringing it into R and then plotting it here pretty quickly. And it's really straightforward and easy. And we'll discuss why bringing it into R can be useful a little later in the talk. But for now, know that we can start just in this web interface and then bring it into R pretty easily, which will be helpful in a little bit. And we'll discuss why then. So yeah, this is just discussing what I kind of just did. I used an example of smoking and lung cancer down below, and you can review that as well. And you can see I did some more stuff to make it more beautiful, making some colors so that they stand out. And so this brings us actually to exercise 1, which is, you've been putting these very excellent causal questions in chat, and I'm sure others of you have been also thinking about it, even if you haven't been putting them in chat. So make the DAG for a causal question of interest, then export it to R using Daggety and or ggdag. Try adjusting different aspects of it, such as position and color. Yeah, and we'll get started. And I'll kind of do my own example another example while we're working on this. So yeah, I think we'll take maybe like 10, 15 minutes to do this. And if you have any questions while we do this, just put them in chat. So I'm thinking about the relationship between the gut microbiome and colorectal cancer. I imagine 2 important variables in this relationship would be diet and age as well. And then I could imagine there's probably some mediators here. For instance, changes in the lining to the gut, or the effects on how the intestines function could be mediators in this pathway. but I'm not going to add those at the moment. But I'm thinking about diet. I'm guessing diet changes the gut microbiome, and the diet, it's possible that, you know, it has some pathways other than just affecting the gut microbiome, uh, where it might influence colorectal cancer. For instance, if it causes obesity, which might increase the risk of colorectal cancer independently of the gut microbiome. So I can imagine there's that relationship there. Age, similarly, you know, your microbiome could vary by as you get older. Um, and then it could also, you know, again, independently affect whether someone develops colorectal cancer. So we can imagine these two variables there. Um, we could imagine some other ones, potentially, you know, maybe exercise plays a role. And when we're thinking about variables that affect human health, you know, there's some other important ones. Gender is often pretty important for these, and so we've got this nice model with with our exposure and outcome and 4 additional variables. And again, I'm just going to take this into R by going to this model code, copy and pasting it, making a new thing. I would load my Daggety library if I needed to, and then I would just save it as an object. We'll call it DAG, and then use the Daggety function, and put the Daggety code in there. I put it in single quotation marks because, as you can see, it uses double quotation marks for the position coordinates. Once we have that DAG object, we can then plot it. So once again, we can see the model I made. It actually looks quite nice. I like how this one turned out. But then we could also use ggdag on that object. Kind of in the basic form, it looks like this. So it's using, again, the ggplot kind of default, which includes, you know, an x and y axis coordinates, which doesn't really make sense for a DAG. So we can turn that up by using one of the DAG themes. There's several of them. There's blank, there's gray with a grid. I prefer the blank theme. Oops, come on. I don't know why it's making them all so small to start, but yeah, you can see that we've got it here. We can change the text color. We can play around with it. So, right, we just need to specify the text color by saying, we could say red. That's a little nicer looking. You can see the variable names a bit better than when they're white. You can specify, you know, different colors if you prefer. And you can change the size of the nodes. Let me see how you do that. Yeah, it's just, you can just add this argument node size. You could say 20. See what that gets us. So a little bigger, maybe a little easier to read. I don't like the yellow. The red actually probably stands out the best. Yeah. But as you can see, you know, you can play around with it, make your DAG nice and pretty, however you want it to look. Yeah, so that's how you make DAGs. How is everyone doing? Are there any questions or comments or issues you're having, places where you're stuck? Feel free to put those in chat if you have any questions. Okay, well, seeing none, I hope making your DAGs has been going well. I'll switch back. I'll start talking again, but feel free again if you have any questions to drop those in chat. So that's DAGs. That was a little bit of a detour. We'll come back to them a little later on in the workshop to discuss why they're useful and why having it in R is useful. But for now, we're going to switch over and start talking about some things you will see on DAGs. So or some sources of bias and error when we're working with in the realm of causal inference that could cause issues as we try to estimate, the effect of some cause or exposure of interest on our outcome of interest. So the most common of these, and the one you probably know about, is confounding. I think we hear a lot about confounding, and I definitely did, early on in my training, but I think rarely we're taught exactly what confounding is. We know it's a third variable that's somewhere in there, but we don't really get the full definition of what a confounder is. Um, and what a confounder actually is, it's something that causes the outcome, causes the exposure, and it's not a mediator. It's not present on the causal pathway in some other way. So it's both causing the outcome and the exposure. So returning to our dog and ambulance example, um, we can think about a third variable that could confound this, a nearby car crash. So we can imagine there's a car crash, an accident, and that causes the dog to start barking before the ambulance even arrived. It is possible that the ambulance also caused the dog to bark more, but what we'll see is that, if the ambulance didn't cause the dog to bark, but because this car crash happened, we might observe a relationship between the ambulance and the dog barking, even when there wasn't one, or it wasn't as strong as we thought there was, just because this car crash happened before, maybe before we started observing the events, or maybe, um, you know, we knew about the car crash, but we didn't know that it had such a strong effect on the dog barking. There's a lot of different possibilities here. And so we can represent this in a DAG. You can see here we've got our car crash. It is both causing the exposure, it's causing the ambulance to arrive nearby, and it's causing the dog to bark. So that is a confounder, and that is how we represent it on a DAG, with an arrow pointing from the confounder to the exposure and to the outcome. And when we have a confounder in our model, our causal model, we say that there is a backdoor pathway. So the front pathway would be the pathway between the exposure and the outcome. So that this is our front door pathway, you might call it. And that's our pathway of interest. But this confounder has created a backdoor pathway, a pathway that goes from ambulance to car crash to dog barking. We trace the arrows. Um, and the issue here is that this backdoor pathway might bias the relationship that we observe between our exposure and outcome. So again, in this situation, we might observe barking and conclude that the ambulance caused it, when in fact, maybe the dog or the car crash caused the dog to bark, or maybe that the car crash made the dog's barking worse than if just an ambulance had driven by. So that is, kind of what a confounder is, but that's a very, concrete, again, example. And what I want to know is if anyone can think of some common confounders in your research. So whether that's bioinformatics or health research or some other related field, just again, put in chat, what do you think some common confounders are? Um, this could be stuff you've adjusted for in the past. It could be some things that you think might be important. Yeah, just think about some common confounders and place those in chat, because there's some that come up quite frequently. Well, I'll start with one while people are thinking. Uh, I think one that comes up quite frequently in health research would be gender. We know that for a lot of you know things we believe to cause a lot of chronic conditions such as diabetes or heart disease, that there is a gender uh, difference. And generally speaking, we can think of something like obesity. There is probably a gender difference there that is both causal of the exposure, and then if we say the outcome is heart disease, that's causal of that as well. Population. Jesu Joba says population diversity. Yeah, there could be differences in the populations. For instance, as uh, Mabandi says, again, apologies if I'm butchering your names. Age group, age is really important. Kevin says environmental parameters as confounder. Yeah, there could be environmental variables that can confound a relationship between exposure and outcome, especially it could be anything from, where like I'm thinking of environment as in like the environment, and that can be an important confounder. People who live near power plants probably have higher rates of asthma compared to people who are further from the power plants. That could confound a relationship of interest. Algorithm scoring functions. Um, yeah, I'm not super familiar with algorithm scoring functions, to be honest, but if that is causing both the exposure and the outcome, yeah, those could definitely be a confounder. Sun exposure, yeah, if you're interested in some kind of either vitamin D or skin cancer, sun exposure could totally cause some confounding. Yes, big one. Socioeconomic factors. That's great, Helen. Yeah, race, income, kind of socioeconomic class in general, wealth, all these variables can confound relationship. Yep, diets, another great one, Malik. Often with microbiome research in particular, diet can be a huge confounder. If you've got some vegetarians versus people who have meat in their diet, that can make a big difference. So these are all great examples, thank you everyone, of some common confounders that we can observe in health research. So now that we've talked about what confounders are and what are some common ones, there's the question of, well, what do we do about it? We want to observe, the true unbiased effect between our exposure and our outcome. How do we get rid of this this confounder, or how do we control for it? Is probably the term you've probably heard the most. Another word for this that I like is deconfounding. And there are a few different ways to do it. The old-fashioned way of doing it would be to manually stratify your data by levels of the confounder. And so in an example where we've got the gut microbiome and colorectal cancer as our exposure and our outcome, we can imagine diet being uh, the confounder there. And what we would do is we would stratify, and we'd say, okay, let's look at people who ate a vegetarian diet in one group. Let's look at people who, eat meat in another group, and maybe, we have another group for people who are vegan, or do some other kind of diet that's separate. And we look at the effect size within each group, and then calculate a weighted average of the effect size across each strata. This is the very old-fashioned way of doing things. It's called a Cochrane mental Hansel statistic. If you paid very close attention in a biostatistics course, you might have heard this mentioned at some point. No one really does it this way anymore because it's a lot of work. You have to manually stratify, then you have to calculate effect sizes, and it's not as flexible. So instead, what we do is a regression model. And so when we do a regression model, what we can do is add the confounder as an independent variable in our model. And by doing that, we have controlled for it. Because effectively, when we add a variable in our regression model, Again, I'm not going to get super into the math behind what we're doing and why. If you are interested in learning more about why this works in terms of um, regression or the math behind anything that I'm saying, I'll have some resources later on that you can delve deeper into. But I'm trying to keep this math free, you know, for to make this simple. But if we add that confounder as a variable in a regression model, so if we imagine a regression model that my independent variables are both you know, some measure of the gut microbiome, maybe like an alpha diversity measure or something along those lines. And then we also add in diet as a separate variable, as probably a categorical variable, where we've got it coded, you know, 1, 0 for like vegetarian diet or not. And we add that to our regression model as another independent variable, with the outcome being, you know, the observed rates of colorectal cancer. And when we add that variable into our regression model, we are doing the same thing as the old-fashioned way. We're effectively taking a weighted average across strata, and we get an effect size that is our beta coefficients. So that leads us into exercise 2. So as you did in exercise 1, you made this DAG for a causal relationship. Oh, um, okay, we have a question real quick. Mbandi, excuse me again, asks, how do you tease apart a confounder from a mediator? And does the process of deconfounding assume that we know the variable as a confounder and not a mediator? That is a super good question. I'm glad you asked that. That's awesome. Yes, that's a tough question. We might not always know if it's a confounder or mediator. What we have to do is, based on prior evidence and then our own knowledge of the situation, as well as the DAG we've created, you know, we need to theorize what the relationship between the variables of interest is. I mean, there are some approaches for testing for mediation. Some statistical methods for that. But ideally what we do is, before we even start modeling anything, we identify what our potential confounders are, what our potential mediators are in our DAG, and we think about that, and then we use that to construct our model of interest and then test it. So yeah, I wish I could say this is how you know this is a mediator and this is how you know it's a confounder. But a mediator would be something, you know, that again that lies on that causal pathway between them, but it wouldn't be a confounder. But we don't know for sure necessarily if that's the case, because we can imagine a situation where we do observe a mediator that looks like a confounder. That is possible, because it could be, you know.
Continue.
Can you hear me? I don't. Yeah. Okay. Uh, yeah. Sorry, my headset keeps disconnecting for some reason. I don't know why. I'm gonna make sure it's plugged in all the way. If this keeps happening, I'll switch to my wired headset. It's in the other room. Is the mediator the same as an effect modifier? That is a good question. I would say no, they're slightly different. So a mediator would be something that lies on this causal pathway. An effect modifier would be something that changes the relationship of this causal pathway across different strata of that effect modifier. For instance, I think an example that I read about recently was effect modification by skin color, between the relationship between sun exposure and vitamin D levels. So in that, skin color modifies the effect of sun exposure on vitamin D levels. But it's not a mediator, right? Because your sun exposure does not cause your skin color but instead the sun exposure modifies the observed relationship between um, the sun exposure and your vitamin D levels. So yeah, I think they're different. I do think there are cases where you can see something that functions both as a mediator and as an effect modifier. Um, that's a little beyond the scope of what I'm talking about today, but I believe if you do like a Google Scholar search for effect modification and mediator, you'll find some papers discussing that phenomenon. These are good questions. You guys are really thinking about this. So this leads into exercise 2. Using your DAG that you developed in exercise 1, consider adding some potential confounders. And then if you could just put in chat, what are some of those confounders that you're thinking of for your particular causal relationship of interest? And I'll give you a couple minutes to do this. You can add them to your DAG in Daggety, or you can just think about them and put them in chat. It's up to you. Okay, headset was having issues. I am on my wired headset now. Can you hear me? Hopefully. Hold on. Yes, perfect. Okay. Sorry about that. So has anyone thought of any particular confounders of interest? Okay, well, we'll keep moving, but yeah, just think about what could potentially confound your variables of interest. Um, we'll talk about one more thing, and then we've been going for about an hour and a half, so we'll take a quick break after this. So the one other thing I want to mention with confounding is the issue of unmeasured confounding. So this is a common issue in observational studies. And so what this is when we have confounding, but we don't have a way, we didn't measure it, we didn't observe it, and so therefore we don't really have a way to include it in our model. Like we can't put it in our regression model because we didn't measure it. It's become a missing data problem, and we can't deconfound for a confounder we haven't measured. Um, and so there's and therefore we have this possible source of bias, and the question is, well, what do we do now? We've got this unmeasured confounder, we have no data on it, and it's biasing our relationship of interest. Well, there isn't really a full solution because, again, don't have the data, but what we can do is conduct a sensitivity analysis. And in this case, what we would do is we would observe how sensitive our measure of the effect size between the exposure and the outcome is to a hypothetical, like a simulated confounder. So we would create, a simulated confounder and put that into our model and see how much that changes our effect size. Um, and if that is changing our effect size by quite a bit, for instance, making it non-significant, um, we could include that in our interpretation of the results and say, well, if we had a unmeasured confounder that was strong enough, our results become non-significant, and therefore we're less certain about how about this model being accurate. There's a possibility that of an unmeasured confounder, and therefore we need to interpret things in the light of that. Um, but yeah, I mean that's one solution. It's not perfect, and it's still possible. For instance, you have to think about how powerful the unmeasured confounder could be. The classic example, I believe, with the smoking and lung cancer, um, that R.A. Fisher posited, that there was that genetic variant, which was effectively a confounder of the relationship between smoking and lung cancer. Um, he he proposed that confounder, and then critics said, well, if that were a confounder and they didn't have a lot of tools for measuring genetic variants back in the 1950s and 60s, so they couldn't measure it directly. But critics said if that were a confounder, it would have to be just such an extremely strong genetic variant that it would be unheard of and how strongly related this variable was to both smoking and lung cancer. And that was kind of how they disproved that thought. Was they said, okay, uh, and I'm doing this in memory, but I believe they said that the confounder would have to nearly be it would have to cause like a tenfold increase in the effect size for it to be biasing the relationship enough to make the relationship between smoking and lung cancer non-significant. So that was effectively a sensitivity analysis they did for this unmeasured confounder. And so with that, we're at kind of just the halfway mark. So I think that's a good spot to take a break for maybe, let's say 5 minutes. So we'll come back at 35 after the hour. Yeah, just have a moment to stand up, stretch, get a drink of water. I know Zoom fatigue is real. So talk to you in a few minutes. And if you have any questions in the meantime, I'll hang out here and look at chat. Okay, so we'll just give people another minute or two, and then we'll get started again. Okay, so welcome back, everyone. I hope you had a nice little break. Maybe you gotta stretch your legs for a moment, have a drink of water, look away from the screen for a moment. I know that's all really important these days. So we're gonna get back right into it since we've got a lot to cover still. Um, so now that we talked about confounders, we're going to talk about colliders. Confounders and colliders seem really similar. Uh, However, colliders are not common causes of the exposure and the outcome. Instead, they are common effects of the exposure and the outcome. That is to say, the exposure causes the collider, the outcome causes the collider, and the collider is not a mediator again. So to compare that to our confounder, um, you with the car crash, we can remember that it both causes the exposure and the outcome, but in our collider, the exposure and the outcome cause the collider. So we can imagine in our ambulance and dog barking example, I think this is the last time we talked about it, or maybe second to last time we talked about it, by the way. Um, you're probably sick of them, of this ambulance and this dog. Um, we can imagine like sleep disruption being a collider. You know, both the ambulance making noise and the dog barking disrupts, you know, if you're sleeping nearby, both of those things might wake you up. Um, and so that's a collider. And so it is not causing either of those variables, like me waking up from being asleep is not causing the dog to start barking. It already started barking because of the ambulance, and the ambulance isn't here because of me waking up. Um, you know, it's there because of the car crash we saw earlier, let's say. Um, so when we have a collider, even though it looks similar to a confounder, uh, we don't treat it the same way. And if we try to adjust for a collider as one would for a confounder by putting it in our regression model or by, you know, stratifying based on that, we might actually introduce bias to our model. Um, because in effect, by so to talk a little bit more about these pathways, if there is a double-headed arrow, so if we see this arrow hits here and then there's an arrow here, if there's two arrows pointing in, that pathway is blocked. So compared to our confounding example, where we see that there isn't two double arrows hitting each other here, that pathway is unblocked by default, but this pathway is blocked by default. But if we add it if we try it and adjust for it or deconfound for it, we actually open up that pathway. Um, so we don't want to do that. We don't want to open, you know, backdoor pathways where we don't already have them. So what is the proper way of dealing with a confounder or with a collider? Uh, don't include them in your model. Ignore them. If we have a collider, it's not going to affect our assessment of the exposure or the outcome. It's just a common effect of both of them. So it should not be adjusted for or included in models. Um, So that is a collider. And why is that important? So this again is just talking, oh, sorry, I'm just going to talk a bit more about pathways. So once again, um, if you've got those arrows pointing into each other, that pathway is blocked. If there are no arrows pointing into each other, they are not blocked. So you can see here again, even if we've got two variables here, C1 and C2, um, they still confound this relationship. We would deconfound by adjusting. We could choose either C1 or C2 by adjusting for one of the variables on the pathway. We have blocked that pathway, so we don't need to control for both. We could control for C1 or C2. This is really important in cases where you have an unmeasured confounder, but potentially you have something um, that might be related to that confounder that's either caused by that confounder or causes that confounder, we can adjust for that instead. So there might be, you know, some variables that are difficult to measure that we can then just adjust for something that causes that confounder instead. In contrast, again, if we have a collider, that whole pathway is blocked. So we do not need to adjust for it. So even if it looks like from here that C1 might almost, it could be a confounder, but nope, because we've got these two arrows at C2 pointing into each other. And that is a collider, and this whole pathway is blocked. We would not need to adjust for C1 or C2. Again, I'm giving you a very high level just quick introduction to how these pathways work. If you want to learn more, I will have more examples of, or more reading and materials for you at the end if you really want to get in the math behind how this works, or more of the theory of how this works. So again, we have an exercise. Think about what might be a collider of the DAG you've made in exercises 1 and 2 of some relationship of interest to you, and add that collider to your model. And I will do the same, since I've realized I haven't added one for my gut microbiome and colorectal cancer example here. So I imagine maybe like poor health could be generally a collider that we observe here, because yeah, we can imagine that potentially maybe the gut microbiome has some impact on your health. Colorectal cancer also has some impact on your health, but potentially, and again, there could be some arguments either way. This could potentially be a confounder. Um, it and it's based on how you theorize the relationship to work, but I could also see it potentially also being a collider where the poor health we observe is just due to both changes in the gut microbiome and colorectal cancer. So a lot of this is there isn't a right answer. There isn't a perfect DAG for any situation. It's just based on what you think it is going on, um, based on your knowledge, based on prior research. And you can see when I add a collider here, the confounders I've added are red. That's because they're important to adjust for. Um, and Daggety notices that and makes them red for you so that like, okay, this could impact and bias this relationship of interest. But poor health stays gray. And that's because it's a collider, and so we don't need to adjust for it. We don't need to deconfound. It's a collider, and therefore we can ignore it, and that's why it's gray. So if you've thought about that collider and added it to your model, I'll give you 1 or 2 more minutes to do that, and then we'll move on. Okay, moving on. We're going to start talking about selection bias. And to start, oh, my image didn't load. I'm going to bring this image in from over here. This is a famous example of selection bias. So to explain the story behind this image, which possibly you've seen before, but during World War II, a statistician was brought in, I believe it's by the British Air Force, uh, and they brought him in and said, okay, we have, you know, a bunch of planes, that are fighting in the war, and they keep coming back with damage. And these are the patterns of damage that we observe. So is this where should we strengthen the planes in these areas? Like where should we put more armor on the plane so that the pilots are protected? And they were originally going to put it where they saw the most damage because they assumed, okay, that's where the most damage is, that's where it's getting hit. But the statistician pointed out these are the planes that come back. They survive the damage long enough to travel back to the airfield and land, whereas the parts where we don't see any damage on those planes are probably the parts where the planes have been hit and they crash. They aren't able to make it back to the to be inspected for damage in the first place. And why is this important? Well, this is an example of selection bias because the planes that returned to be assessed for damage were different from the planes that were taking damage during the battles. If we can assume, that the damage was fairly randomly distributed on the planes, the parts here where we see like the engines, the tip of the plane, this part near the tail, if they took damage there, that plane wasn't coming back. And so that was the area that they needed to add more armor to and to improve the protection of, not the areas that were taking damage. And that is an example of what we call selection bias. Also, you've maybe heard of survival bias. And I think we're often exposed to this term like confounding, but we're not actually told what it kind of means from a causal perspective. And what's actually happening in selection bias is we are accidentally uh, conditioning or stratifying on a collider. We're not doing this on purpose. We didn't purposefully decide to have certain planes come back and some uh, to not come back, but it happened by accident because of the way we designed the study. So we have accidentally, by the way we have designed our study, selected people for the study based on a confounder, or not, excuse me, based on a collider. As a result, we've introduced bias, and there could be bias between our exposure and outcome. One faculty member of mine calls this the already dead problem. Um, and people who, and I find that just to be the greatest way to remember, because I always think the already dead problem. People who have already died of the outcome are not alive to be in the study. And these people may be different. They might have had, a greater exposure to whatever the issue is. And they might have a more serious or aggressive form of the disease, and not including them therefore biases this relationship between exposure and outcome. So to give some more examples, because I know this can often be a little difficult to grasp, it is for me, there's a lot of studies of people who work in coal mines. Yeah, it is confusing. So let's think about people who work in coal mines, and a lot of them develop emphysema and other lung conditions. You get the coal dust into your lungs, you breathe it in, you get sick from different conditions of the lungs. Um, so what a lot of these industries in the United States will do, at least, is they'll do studies and they'll say, well, but look at our workers. All our workers are perfectly healthy. They're not developing emphysema or other lung conditions. And the issue with those studies is that the workers who did develop those conditions have already, they're too sick to work. They've dropped out of their job. If I have emphysema, if I have lung cancer, if I'm having a condition like that, maybe I can't really go and work in a coal mine anymore. Um, and so this problem is called, you sometimes hear it called the healthy worker bias. in that case, where the people who are around to be studied in a kind of a workplace are the people who haven't gotten sick. Um, and that's another form of selection bias. Um, One additional example that comes up in health research is you often see this paradoxical relationship between obesity and mortality, where it seems like people who are overweight and obese in certain age groups are actually less likely to die than people who are normal weight or underweight. And the cause of this kind of paradoxical observation, given that we know that obesity seems to be linked to several negative health outcomes, such as heart disease, high cholesterol, potentially other conditions as well, is that people tend to lose weight before they die of a lot of chronic conditions. People with cancer lose weight. People with other chronic conditions will tend to lose weight. And therefore, depending on the timing of when you collect the data, you might introduce selection bias in that you observe people who have lost a bunch of weight and then they end up dying because they were already sick when the study started. And therefore, that's kind of another form of selection bias where you then observe a paradoxical relationship between weight and mortality. And so these are all kind of examples of survival bias, which is a form of selection bias. But another common source of selection bias is loss to follow-up in many studies. Particularly in studies where you're testing out like a new medication or a new treatment, what you can see is that people who don't like the treatment, maybe they have bad side effects, maybe it doesn't make them feel better, maybe they're more likely to drop out of the study and be lost to follow-up. We can't collect more data from them if they're lost. Um, and they drop out of the study at a higher rate because they're having these issues, and therefore we observe a biased relationship of our treatment. Like, let's say it's a new cancer medication, but it causes really, really bad nausea, and some people just cannot stomach it, and they drop out of the study. And because we lost them, we can't assess how they're different from the people who weren't lost. And again, this creates kind of a missing data problem that then biases the relationship between our treatment and our outcome of interest. So that's probably the most common and uh, pervasive form of selection bias that you will see in a lot of different studies. Um, and that leads us to a question. Is the collider you added in exercise 3 a possible source of selection bias? If so, how? So I'll again go to my DAG where I look at poor health as a collider. And I think depending on how you design the study and at what point you recruited people, this could very easily be um, a source of selection bias. For instance, if people in the study, if they eventually die due to their poor health, this they're not alive to be recruited into my study, and therefore I might not observe the correct relationship between gut microbiome and colorectal cancer because I've selected on people having a less aggressive form of colorectal cancer or better health in general, and the people with poor health have already died and haven't lived long enough to be in my study. Um, I could also see an example where people with uh, uh, particularly poor, gut microbiomes and particularly aggressive colorectal cancer maybe don't want to participate in a study. They're not feeling well. They've got poor health, and therefore they don't agree to consent to be in my study because they just want to focus on getting better. And again, we've inadvertently, introduce some selection bias. Um, so I think that's kind of the classic example. Does anyone else have any examples you're thinking of what might introduce selection bias to a study, whether it's something of interest to you or just in general? Feel free to put those in chat. Okay, well, I think I covered the major one, which is poor health and death, but there can be other cases. For instance, hospitalization is an important one. If people are in the hospital and you're recruiting only people who are in a hospital or not in a hospital, that could be a source of selection bias. Um, yeah, so those are probably the most common ones, and it's important to just think. Yeah, Francis, I will provide some additional materials at the end that will go into this in much more detail. You know, part of my education has been entire classes where, you know, for an entire semester where we focused on selection bias. So I'm giving you a very brief overview, and I'm avoiding going into a lot of detail, but there will be some resources at the end um, that provide additional background and information and a, enough math that will tons of math behind all this as well. If you like math, I've been trying to avoid that. But you, if you like the math portion of figuring out how selection bias works and how that bias would actually affect the relationship, that will be available. Uh, so real quick, I'm going to review some study designs from a causal inference perspective, and then um, talk about why this is important. And I think you've been introduced to a lot of these, so I won't focus on them too much. Um, but real quick, so probably, you know, the form of study design that we're all the most familiar with would be a randomized control trial or randomized clinical trial, an RCT. As you're probably aware, the exposure of interest is assigned at random. You know, you're given um, a treatment or uh, uh, you know, a medication or something else at random. And because the exposure is assigned at random, there are no possible confounders of the relationship between the exposure and the outcome. Because if you remember the definition of a confounder, um, it has to cause the exposure. But if I am flipping a coin and saying, okay, those of you who I got a heads on, you know, on this coin, you get the treatment, and those of you who get a tail get a placebo. There's no possible confounders. You know, the age could not confound that because I assigned it at random. You know, gender could not confound it; it was assigned at random. Um, as a result, this also means there's no possible unmeasured confounders as well, and that's really important. And that is why RCTs are considered the gold standard for causal inference. For instance, you know, with the COVID vaccines, you know, they all of them had clinical trials that were randomized. You know, some people received the vaccine, some people received the placebo, uh, and using that, they were able to conclude, you know, people who got the vaccine seemed to be protected against coronavirus relative to people who got the placebo. And they were able to make a very strong causal argument that the vaccine was working because there was no possibility of confounding. However, selection bias is still possible. So based on what I kind of just talked about, any ideas on how selection bias can occur in an RCT? Feel free to put them in chat or yeah. I realize this has gone on for about 2 hours and I still have an exercise to do. So I'm going to move fairly quickly through the rest of the material so we can at least get into R and talk about the exercise a little bit. So the principal cause of selection bias in an RCT would be loss to follow-up. You know, again, as I said above, you know, people may not tolerate the treatment and may drop out of the study, and that can introduce selection bias. That was not so important for like a vaccine trial, of course, because you're given the vaccine and you can't really opt out. You received it, you know, at the moment you were randomized. But in trials of longer term medications, this is a bigger issue. For instance, I believe a lot of trials of different hormone replacement therapy that was given for women undergoing premenopausal symptoms. They tried HRT as a treatment to help alleviate some of those symptoms, but they were finding that there was significant selection bias because the 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 hormone replacement therapy could cause some women to experience side effects, and they would drop out of the study. And therefore introduce selection bias, which is part of the reason why there was a lot of uh, excitement around HRT in the 90s, and then it's kind of pretty much been discontinued as a treatment at this point. Once they accounted for selection bias, they started realizing that it didn't seem to be as powerful as they thought. Related to RCT is the idea of instrumental variable analysis or Mendelian randomization, which is often what you hear referred to in bioinformatics. This idea is that you use some kind of source of pseudo randomization, something that can work as a randomizer in a case where you can't do an RCT, perhaps because it's unethical or yeah, it's logistically impossible. So in this case, if we look at the DAG for an RCT, the exposure is assigned by coin flip, and therefore there is no possible way that there can be a confounder. There's no way that something can cause the exposure because we've assigned the exposure at random. In Mendelian randomization or instrumental variable analysis, the coin flip is replaced with some source of randomization, such as just a randomly distributed genetic variant, or we assume it's randomly distributed, or some other variable that we assume to be kind of random or pseudo-random. And researchers have used a variety of factors. So a very common one you'll see is before and after implementation of a new government policy. For instance, uh, uh, a very common one is like if they change health policy in some way by, say, introducing a new subsidy for a certain medication or a new standard of care, then you can look at immediately before and after that implementation of that policy. Um, Another common one is distance from a medical center. So people who live further from a medical center are less likely to go there for treatment unless it's serious. So you can use that kind of as a randomizer if you're interested in um, that. And then genetic variants. So again, this is, we assume the genetic variant is kind of randomly distributed in the population. And then we can look at that genetic variant if we know that it causes the exposure um, to see if that genetic variant can help us make more stronger causal arguments without doing an RCT. And so this seems pretty powerful. Like you look at this and my thought is like, wow, we should be doing more of these. But there are some issues with them. And again, I'm just going to answer my own question here. So the issue is that it needs to be something that is actually random or pseudo-random in a real sense. And that is the big issue, is finding some source of randomness. Okay, let me see what Kevin is saying. So for example, conducting a drug treatment for a population of an endemic area of schistosomiasis to see the effectiveness of the treatment by following the intensity of the infection can have issues of two selecting bias. Yeah, so I think there could be selection bias in that case where the effectiveness of the treatment and the intensity of the infection could both cause selection bias, because if the treatment is not very effective, um,
Hello?
or people are having really bad side effects and they drop out, that's definitely one thing. And the intensity of infection, if people have already died, hi there, we've got a child with us. Hi there. Um, uh, yes, exactly. Yeah, and that would be selection bias. Some people are not providing samples, or they stop taking the treatment. Kevin, those are both great examples of selection bias. Thank you for sharing that. I totally understand what you mean. So real quick, we'll go into observational studies. So these you're probably familiar with as well, but maybe haven't been exposed to them by name as much. So cohort studies, these are studies where you choose people with a common characteristic, such as an occupation, a location, or a history of a particular disease, and you follow them over time, where you then assess them for various exposures and outcomes. So I'm involved in actually a big cohort study of coronavirus,
Oh,
where we've got about 7,000 people across the United States, and we started right at the start of the pandemic, and so the vast majority of them at that point had not had coronavirus, uh, but we followed them over time. And over the past year, I would say about 5 to 10% of them have subsequently developed coronavirus. And so now, since we've been following them since before they got coronavirus, we've got kind of a wealth of data on what they were doing, what kind of risky behaviors they were engaging in, and therefore we can really study that that potential for risk versus developing coronavirus, and then also seeing how they react to coronavirus long term, and how their symptoms have played out. However, this is an observational study. Selection bias could occur,
hi,
both
my
based on
friend.
hi, both based on loss to follow-up and based on confounding. There could be both things that are associated or that are causal with the exposures and outcomes of interest. We didn't randomize them in a cohort study. It's observational. We couldn't really design an RCT of coronavirus. It'd be pretty unethical, I think, at this point to say we're going to give half our population coronavirus and half won't get it, and we'll see how they react over time. That would be pretty unethical. Don't think you would find very many, ethics boards that would be okay with that kind of study. Um, Another type of observational study is a case control study. So whereas in the cohort study, we kind of start and follow them over time, what we do in the case control study instead is we choose people who have the outcome of interest already. So this could be people with diabetes, people with colorectal cancer, people with, the condition of interest. And then we match them to people who are similar. So we'll often match on age, sex, race, socioeconomic status, other variables. We try and make them similar because the goal is to reduce the number of potential confounders. So we try and match them to someone very similar to them. Um, and then we look backwards and say, okay, what are the differences between our cases and our controls in this case control study? And where did they differ? And how does that affect them? So we might look to see how they differ on exposures of interest. Um, so a very classic example of this will be like twin studies. So those are case control studies. So generally speaking, you look at one twin who has the disease and one twin who doesn't have the disease. And you assume because they're twins, they're probably very similar. And you look backwards and say, okay, so we know they're twins, they're very similar. How are they different then? And then finally, there's the genome-wide association studies, which again come up in bioinformatics. These are observational studies of phenotypes where you look across a large chunk of the genome to see what's associated with them. Um, and they can be a case control study or a cohort study. Some of them, they do choose a disease of interest and then try and pick controls, or they do a whole cohort of people. And just as they are observational studies, you can have selection bias and confounding in GWASs just as you can in case control and cohort studies. Okay, so that was a quick survey of study designs. We're going to get into the exercise shortly. So again, we talked about this very in-depth theoretically, but I want to give you some practical guidance in terms of, okay, how do I go from I've got a research question, it's got a, I've got a causal question that I'm interested in or that I want to look into more. How do I go from having this question to testing it? Well, as we discussed, we can make our DAG. So this is we talked about Daggety, you can make your diagram and bring it into R. So this is just another example of that. But the nice thing we can then do in our, if we have got a very complicated model, and this isn't even that complicated, we only have 7 variables, but we can imagine situations where we have a lot of variables, biological systems, and can be very complicated. And so there could be dozens of variables. It might be really difficult to tell what to adjust for because, as I mentioned, you don't need to adjust for colliders, and you only need to adjust for one variable on a backdoor path, a confounding pathway, if there's multiple variables on that pathway to block that pathway. So instead of relying on trying to like sit here and figure this out and say like, okay, well, X is my exposure of interest and Y is my outcome of interest. Let me start tracing pathways. That's a lot of work, and why not have R do it for us? So this snippet of code right here, which you can run for yourself or just look at this vignette. What this will do is it will tell you what you need to adjust for. And using the DAG, which we call G1, you can see it's G1 up here. It's just the DAG, and we just feed that into here, and it says, okay, here's how to adjust for everything. We're interested in X on Y, so we'll look for X on Y. We find it here, and it says, okay, I can figure out the effect of X on Y. It's identifiable, is another way of saying that, by controlling for any of these sets of variables. These are called adjustment sets. So some cases you might only have one adjustment set, which you can see for some of the other variable pairs down here. But in this case, we've got 4 different options. So we could adjust for W2, Z2, V, W2, etc. So we've got 4 options, and if we adjust for any of these 4, you don't have to adjust for all of them, just one of them. So we could just pick one, adjust for that, and if we have specified our DAG correctly, we will be able to then get the effect of X on Y controlled for any potential confounding from the variables in our DAG. This line of code though, or this block of code though, is a little, it's a lot, and it's giving us a lot of additional information. We're not very interested in these other variables. So ggdag actually has a very nice function called adjustment set. And in that we just give it our DAG, our exposure variable, and our outcome variable. And then it will give us these nice little charts of what we can adjust for. And I will show you this using one of the samples I made. So this was the one with the, actually, let me take the newest version of this into there. Again, just pasting it in there and using this Daggety function. And then we can just say ggdag adjustment set. My DAG is called the DAG object. My exposure is called gut microbiome, and my outcome is called colorectal cancer. And if we do this and make this bigger, we get a model that tells us that we need to adjust for, and we can put the text color, I think might be helpful. Yeah, a little easier to see. Make this bigger. We can see it tells us, we don't need to adjust for any variable in blue. We do need to adjust for variables in red. So poor health, as we remember, is a collider. So we don't want to adjust for that. But gender, exercise, age, and diet are all confounders, and we want to adjust for that. This is a pretty simple case where there's only one adjustment set. But as we can see in here, this again is using this more complicated DAG. There's 4 possible adjustment sets, and it gives us each of these as a separate chart where we can see where it tells us to adjust for them. And they are in red. And these are the same, this is the exact same thing that we got above here, but just depicted graphically. So I like this, it's really neat. Um, So adjusting for confounders, as I mentioned, to deconfound, you just include them in your regression model. I have some examples here for some common packages that I use in my research. DESeq2, it uses a negative binomial regression model. So when you are specifying your model, you can just include the confounder as a independent variable in the model. Edjar and Limma, which are again both packages. Yeah. So the DEC code, Anita says SE is unknown. These are just examples. They're not run. There's no data behind these. We'll do an example in when we do the exercise in just a moment. Yeah, because this is not. These aren't real variables, and there's no data set for this. I'm just showing you what this would look like. Edjar and Limma similarly, you can specify a confounder, which would be this batch variable here in your model matrix term, which is then just fed into your Edjar and Lemma models. So yeah, that's how you deconfound. Selection bias is a bit more difficult to control for. We can't really control for it. It's kind of a missing data problem. We'll discuss some options for that in a moment. But I have an exercise which we can do together. I'll probably do it and you can follow along with me, or if you want to like just go off on your own and try it out yourself, uh, feel free as well. So we'll be using curated metagenomic data, which is a nice source of some pre-curated and ready to go microbiome data sets in Bioconductor. And we'll be using specifically, there's a data set in it, the Vachman E2016 data set. This is from a study of colorectal cancer. It was a case control study. And it had excuse me, it had 52 cases of colorectal cancer and 52 controls. And so we're just going to go through this kind of step by step. So first we'll create a causal diagram for this relationship. So I'm going to go here. I've already kind of made one here. So just to save a little time. So we've got this model. I feel pretty good about this. There's probably more complexities in real life. You know, there's probably more potential confounders. There's probably some sources of selection bias. Yeah, sorry. If you're using the one that's on the 2021, that's on the uh, what was it called? The system, it might not be in there because I have on orchestra. Yeah, it might not be there. You can follow along here. Let me just put this in chat. And then you can get the latest version of the workshop materials if you want to clone it from GitHub or there. Yeah, sorry, I've added this example in yeah later. So I constantly futz with what I'm doing, so this was added later. So I apologize that the materials aren't the most latest, but you can just follow along with me. So I've created this DAG. There could be more variables here. You know, we've got possible source of selection bias. There's other possible things that could be going on there. But we've made this DAG. We can bring it into R, which I've already done, and then I can get my adjustment set, which is what we've done here. So we've kind of done this first step, which is creating the DAG and looking at what our variables are in the DAG. And then in the next step, well, we've created our DAG. We've determined what to adjust for. Now let's download the data and take a look at it. So in curated metagenomic data, so in the GitHub, there's also this demo.r file, which you can use to follow along. But we'll be using a few packages here. We'll be using curated metagenomic data, which is available on Bioconductor. The installation instructions are above. Daggety, DSeq2, PhyloSeq, and ggdag. So once again, let me just load all those. And then we'll create our DAG. This is a simplified DAG based on the variables that are that I was thinking about when I made this. So here's the first version of it. It's a little confusing. The one I made over here I think is better. But then we can get the adjustment set for this as well. Again, this is yeah, we've got diet, gender, health status, age. In this case, I used hospitalization as a potential source of selection bias. But again, it's based on what you theorize, and it can change. Different people might theorize different things. So the next step is to download the data. So that's what will happen in step 2. So we use this curated metagenomic function. We tell it the name of the data set we want to download, and we tell it we don't want to do a dry run in this case. We want to actually download the data. This takes a moment because it's not too big of a data set. I tried to choose one that wasn't that big, but it might take a moment depending on your internet connection. So now we've downloaded that data. We can see, we've got this this object, the Volkmann object I've made here. I want to just extract the expression set from this. By the way, curated metagenomic data uses expression sets. If you're familiar with Bioconductor, you also know that there are summarized experiments which are a little easier to use than expression sets. The newest version of curated metagenomic data will use summarized experiments, so this will change slightly, but for now we're using an expression set, which is just a different type of kind of data object here. So we get that expression set, and then that has a bunch of information. So about, our data. So we can look at this and say, okay, well, I want to know, what is the information on their study condition, that is their health condition. And we'll just do a quick table of that. And as I said before, we have 52 controls, 52 people with colorectal cancer. There were 6 NAs because these people weren't they weren't able to assess the health status, or something else happened. So we don't want to include those people. We don't know their health status, so we can just remove them by selecting people who don't have an NA for that variable, and we'll just do the table again and see that we got rid of those 6 NAs because they don't have they're missing that. And so next, we've gotten our data, we've downloaded it, we've checked to make sure it's got the study condition of interest, and then you can also, look at the other variables that we have here for things that, correspond to the confounders I want to adjust for. So again, I want to adjust for diet, gender, health status, and age. Well, I look here and I don't see a variable for health status. I don't really in my variables that I have access to, but I do see age. I see gender. I don't see diet. So unfortunately, those are unmeasured confounders in this situation. So when I discuss my results, those would have to be limitations. I would have to say, well, I theorize that diet and health status are potential confounders of this relationship. And because I did not measure those, or the data I'm using did not measure those, they could potentially bias the results I see. But moving forward, we can still, run our model using what we do have access to. So the first step I'm going to do with these, the first model rather, is going to be just a general model, a bivariate model, looking at microbiome as a function of my study condition, colorectal cancer. So to do this using DESeq, we first need to convert our expression set to a phyloseq object, and then convert our phyloseq object to a DESeq2 object where we specify the outcome, which is the microbiome, the and then our exposure, which is colorectal cancer. We get a warning message. It just converted study condition into factors, which is fine. And then we tell it to actually, run the model. And we keep, I think these parameters are default. We just do a walled test for our regression model, and the fit type is parametric. You can, depending on your assumptions, you can try different tests and different fit types if you believe that there's like a non-parametric relationship. And so we run this, it fits our model, and then we have some results, and we can look at these results. If we look at them right now, we've got, because it's the microbiome, we've got a lot of different microbiota in here, 1,296 different rows of bacteria. And we can see, we've got our, the results from our model. So we've got the base mean, the log2 fold change, which is our effect size, and our p-value. However, and an adjusted p-value, because we adjust for a false discovery rate because we're doing so many tests. But, we don't want to look at all 1,296. So let's just cut it off and say, if they have an alpha, like a p-value less than an alpha of 0.10, then we'll look at those results. So that's what I do here. And then I get a list, and I bound the names of the different taxa to it just so it's easier to read. So just doing this bivariate result where I just look at the relationship between colorectal cancer and different microbiota in the gut microbiome, I get 5 significant results listed here. Again, I am very bad with names. Escherichia, Ruminococcus, E. coli, another Ruminococcus, another unclassified E. coli. And we can see, we've got our effect sizes, and we've got our p-values and our adjusted p-values, none of which are significant at 0.05, but are significant at 0.10. And then some additional information of kingdom, phylum, class, etc. So this was just a bivariate comparison. So really all we did was test the exposure and the outcome. But we don't want to do that. We want to adjust for our potential confounders. And so in this next step, we add in to our model. So up here, we just specified study condition, but here we add age category and gender to our model. And so once again, we kind of go through these steps where it fits the model, and we get some results, and we can look at the results. And once again, it's going to have a bunch, 1,296 again, because it's the same data set. And a lot of them are going to be non-significant, as we can see here, even when adjusting for false discovery rate. So instead, again, we'll take an alpha of 0.10, and then we'll look at what's still significant after adjusting for age and gender. And we see, in contrast to the five taxa that we saw in our bivariate model, now that we've adjusted for age and gender, only 2 significant taxa remain. Ruminococcus and another Ruminococcus that's unclassified. So I assume those are probably similar, if not the same. I'm not sure. I would have to, and this is something where I need to go and look these up and see if there's any information about what these bacteria are. But I've got my effect size measures here, as well as my adjusted p-values here, and my regular p-value next to it as well. And so I have effectively tested for the model for the confounders I could adjust for, and saw that it did change my results. I saw more significant results in the unadjusted model compared to the adjusted model. And if I feel like my adjusted model is a good fit for what I believe the actual kind of causal mechanism to be, I could I could state, like I believe that colorectal cancer, causes a change in the microbiome and specifically causes a change in Ruminococcus torquus. I don't think I feel super comfortable saying that in that strong a language because I know that I had two confounders that I didn't measure, diet and health status. And I also know this is an observational study, therefore there could be many other unmeasured confounders as well as selection bias. But the important part is that I've identified what my assumptions are using the DAG, and I have tried my best to adjust for that. And so when I now, go to write my paper for uh, this study, I know what to talk about. I know what my limitations are. I know what my research question was, and I know what my findings are and can interpret that in the context of the limitations. And that's really, to me, uh, the best part about this is that it really helps you in writing those papers because it's given you a very clear framework in terms of what to talk about in your methods, how to talk about why you chose the variables that you did as confounders, how to discuss your results, how to discuss your limitations. And we've done all that just by making a diagram and then trying to our best to test that diagram. And to me, that's the power of what we have done. So again, this is just what we just did. Um, and so what we have done is we have found that colorectal cancer is associated with an increased abundance of two taxa. And as I was saying, probably hesitant to argue that this was a causal relationship or that we're very confident that this was causal because there's other sources of bias, as I mentioned. Yeah, so sorry, with that, I've got two discussion questions and we've got about a half hour left, so this is perfect. So we'll go into these discussion questions and then we can wrap up with my conclusions and parting thoughts and then some additional resources. So my first question, because this is something that comes to me a lot, is that sometimes, I'm lucky and I'm able to be there at the beginning of the data collection process and to give input on what variables we should collect data on. Other times, as analysts, we are given data and told, analyze this. And even other times, sometimes we're just sent to a nearly finished analysis for a paper and asked for feedback. And so my question for you, if you can give some thoughts, when during the study process, should we create a DAG, whether it's at data collection, the analysis step, somewhere in between? And is it too late to make a DAG if the analyses are nearly completed? And if you have thoughts on this, please put them in the chat because yeah, these are questions I think about, to be honest. So if you have any thoughts, please put them in chat. I know it's the last 30 minutes and maybe you're tired. Yeah, Kevin says, for me, the best shot should be in the beginning, but it's never too late to build a DAG. Yeah, I think that's good. Depend on the study design. Yeah, I think that is true. Best at the beginning, but can be done at any stage to clarify. Yeah, I, I don't think there's a right or wrong answer to this question. It's something I think about. I think, yeah, if we can create a DAG, there have been times when, I was just sent a paper to review, like they just said, like, can you take a look at the results, make sure, nothing seems wrong, and then we're going to submit it in 2 days. And I kind of look at their paper. I'm like, okay, I'm going to make a DAG based on what they're doing and make sure that it makes sense to me. And yeah, and Winfred makes a really good point. It actually can help you in providing constructive feedback when you're sent a paper to review, because if you make the DAG, then you can think through, okay, these are the assumptions they're making. Are they talking about these assumptions, that they're making, either, in their methods or limitation section or somewhere, you know, um, and are based on this DAG that I've made for what they seem to be testing, did they model it correctly? And these are questions you can ask even when you're just reviewing a paper, even if it's just for a journal. Um, maybe you're not even an author on the paper, you're just reviewing it for peer review for a journal, and that can be helpful in guiding them. And I've often found you can even send DAGs to people as part of your peer review comments, and just to get them thinking about what they're saying, because often people have not necessarily made a DAG for what they've tested. So that can be helpful as well. So yeah, great answers. Um, and so for our second question, I didn't talk about generalizability or transportability at all. So that's the idea, that we've done this study in a sub population, a sample of the population, but then we need to apply the results to an external population. Uh, what issues might arise when doing so? And can you think of any ways a DAG could be used to resolve these issues of generalizability and transportability? I do think this one is kind of a tough question because, again, it's a question without really an answer on generalizability or transportability. Uh, but one thing I think about with this is, often the issue is that your sample is different from your population. Like rarely do we do a random sample for uh, a health condition, often because it's prohibitive if you've got a rare health condition to sample an entire population to try and get enough people with that condition. Or, if you're doing an RCT, I don't think I've ever really heard of an RCT that used a random sample. So they've often used, an intentionally recruited sample of participants. And therefore, if you've taken a basic statistics class, you're often told, okay, well, if you didn't take a random sample, you can't really apply that to the population it was sampled from because it's going to vary. Yeah, exactly. As Kevin's saying, the applying population can be different from the one you sampled from. Um, and Winfred, yes, this is a great example of how a DAG can be used to resolve some of these issues. So if we assume, that there's an ethnic or racial variable in our DAG that we believe affects the causal mechanism in some way, we can actually use that and say, okay, well, I know, from my data, here's what the racial and ethnic makeup of my sample is. And, generally we have some statistics for like a population of a country. Um, in in the US, like we have the census here, where we have some like population level statistics of how many people are white or Hispanic or Black or other races. And so what we could do is maybe, if we look at our DAG and say, okay, races seems to be an important issue, and we can then say, okay, well, if my study population had the same racial breakdown as the population of the country of interest or the area of interest, how would that change the observed effect size? And we can actually model that by weighting our sample accordingly. Again, I haven't gotten into how we would do that. That's kind of beyond the scope of this little workshop, but it's something you could do. And so again, I think a DAG is really useful in seeing what we're assuming and how do those assumptions translate to the larger population, as Winfred and Kevin are both saying, which were excellent answers. So to wrap up, I'm sorry that I couldn't come in here today and say, here's epidemiology and causal inference, and here's how we solve any problems of bias and confounding. Here's the R package. Just use this and you're good to go. Unfortunately, it's not that simple. Instead, when we're doing research, when we're being scientists, we have to think about it. We have to think about what assumptions we're making, what we're trying to answer, what the question is underlying our study, and think about how we're going to answer that question and the assumptions embedded in that answer. And that's why I think DAGs are so important, because they are providing this visualization where you say, here's this causal system that I believe to be important, and it helps you identify confounders and other sources of bias. And as Miguel Hernan, who is kind of a famous epidemiologist, says about DAGs, you're drawing your assumptions before you draw your conclusions. And in doing so, it really helps you frame what you're talking about. And as I mentioned, issues like unmeasured confounding and selection bias are effectively missing data problems and are particularly difficult to deal with. And because they're not measured, it can be really difficult to deconfound or adjust or uh, alleviate the issues of selection bias and confounding. But um, we know our assumptions and we know what we've made, and we can frame our findings in those assumptions, and then also think about in the future how we could avoid the problems that occurred in the past. For instance, by suggesting a way to a new study that will hopefully alleviate some of those problems of confounding and selection bias. And finally, I just want to emphasize it's important to remember that our causal inference is rooted in this definition of a counterfactual. And our goal is to see, how close can we get to making our study so that we are observing what would have happened if a participant's exposure had been different. And that is, in the end, our goal that we are heading towards and striving. Um, so I just want to recommend some further reading and materials. Again, this has been super basic. I didn't get into a lot of the math behind this. There's a ton of math that can honestly goes very over my head. I don't understand some of it, but that explains why this all works the way it does, and how these everything from how a confounder affects your estimate of the causal effect to selection bias, all that. There's lots of theory and math behind it. But my recommendation, if you want to learn more, there's a book by Pearl and Mackenzie called The Book of Why, The New Science of Causal Effect. It was written for like a very, it's a very easy introduction. It's very fun. I consider it like one of the best books if you're interested in learning more about this, but don't want to like I don't know, like intensely study it, but just want to have a little more context. That's a great book. Um, there's also a free textbook available online. Hernan, the epidemiologist, and another epidemiologist, Robbins, published a textbook called Causal Inference. Make this a little bigger. It's available free online. You can get the whole book. It's a textbook. Again, it's a lot more detailed, but it's talking about the same thing I talked about. But you can see there's a lot more of the math in here, explaining more of the mathematical basis of a lot of the things I'm talking about. And it's free and it's a great book. Pearl, who is kind of one of the people who really pioneered a lot of causal inference research, wrote a book called Causality, Models, Reasoning, and Inference. This book is probably the hardcore version. If you really are interested in this and really want to dig into the theory and math behind it, Pearl is a computer scientist, and it is very heavy, and I will say it's not a very easy read, but if you really are into this, that book is great. And then also, as a companion to this textbook, Hernan has a free edX course, so one of these free online courses that's available as well that you can enroll in. It's free unless you want a certificate, which does cost money, but this will give you some videos from Hernan, he's an amazing speaker and a very, very great lecturer. And so you can take this for free as well. And so, yeah, those are some further materials. Thank you all so much for attending. This was, I absolutely adore giving this workshop, and I was so grateful to be here and to give it and to talk about this. And yeah, if you have any questions or comments, feel free to put them in the chat. Thank you so much.
Thank you so much, Chloe. That was very insightful and interesting presentation. Yeah. I think
Thank you.
we have Michelle Skelton on the call. Michelle, are you there? Yeah.
Thanks so much, Francis. So I just wanted to do a vote of thanks to the group. The Bioconductor group is certainly a passionate group of individuals. And I just wanted to say thanks to Chloe Mazzei and Levi Waldron, all the trainers and speakers, Sean Davis, Benjamin Keynes, I hope I'm getting the pronunciation right, and also to Jacob Adam, who really was determined to pull H3Africa in and get this workshop off the ground. Just to thank Bioconductor, they're a really inclusive organization, really pulling H3Africa into the fold and bringing this very useful workshop to us. I know you've worked with the Bionet before, but we really thank you very much for this installment of training. We've had 3 trainings this week, and this is the last of the 3 trainings. We had science communication, research management and administration, and now the introduction to the bioconductor and bioinformatics. So thank you so much. This has really been a great week. And I'd like to also thank from the H3Africa H3A Bionet side, Francis, you've been awesome, really pulling all of this together with Suresh, Pabalo, and also Farina and Confidence. So just thanks to everyone and to all the attendees. We hope you benefited from this. And we hope to obviously work with the bioconductor in future. Thank you so much.
Thank you. Thank you so much. Yeah, and if you just have any questions, also feel free to email me. My email address is at the top. Thank you all.
Yeah, so we'll put the recording on the H3Africa YouTube channel, and then we'll share with everyone as well. Yeah, great. So I think we call it off for today. Bye, everyone.
Yeah. Have a nice
Goodbye.
day. Bye.
Yeah.
Bye.